Good morning, my dear all students. Today our topic of discussion is testing of DC machine. So before starting this topic, it may arise in your mind that why this testing is necessary, why we have to study it. So when we are going to use DC motor in case of different application, in such cases we have to know the efficiency of DC machine. It's a very important factor, because without knowing the efficiency of the machine, you cannot use it for different application purposes. So by testing the DC machine, we can know the input power, output power and different types of losses which occurs in machine, and correspondingly from there we can calculate the efficiency of the system. So before starting about this efficiency, and rather to say the testing of machine, I just want to remind you about the different types of losses occurs in case of DC machine. In case of DC machine, there are different types of losses. As already I have discussed in class, there are basically three types of losses: iron losses, copper losses and fixed losses. Iron losses includes hysteresis loss and eddy current loss. Simultaneously copper losses will be there in armature, and similarly there are constant losses which can be again of two types. One is frictional loss and another one is windage loss. Now let us start about the testing method. First of all, I am just going to discuss with you about the direct method of testing. In this method, the DC machine is loaded directly by means of a brake which is applied through a water cooled pulley. Now here the input and output can be directly measured, and the efficiency can be determined by using the formula corresponding I have shown in this slide, that is N equal to output by input. But practically it is not possible for case of large machines. So for the large machine we are having some alternative method. So for the alternative method we are having here Swinburne test, Hopkins test, and there is another test which is known as braking test. But this Swinburne test specifically cannot be used in case of DC series motor. Why it cannot be used for DC series motor, later on I will discuss with you in this topic. Okay, so first of all I am just going to start about the brake test. So this is a basically pulley or spring balance type of loading. Those who have done the laboratory experiment associated with DC shunt motor, I think all of them have seen it. This is basically a spring balance. W1 and W2 are the spring, and by tightening any one of the spring balances, we can increase directly the loading on the motor. This is the pulley, and with the shaft of the motor, this pulley is adjusted by using a conveyor belt. Now, how the losses can be calculated here? First of all, this W1 is the reading of the one side of the pulley, like the suspended weight in kg. Similarly, W2 is the reading in the spring balance in kg. R is the radius of the pulley. Now, N is the speed in RPS. Whose speed? Motor speed. V is the supply voltage and I is the full load current. Now across the input terminal, whose input terminal? Motor's input terminal, we can directly connect a voltmeter in parallel, similarly an ammeter in series. So that ammeter and voltmeter will give you the reading of corresponding supply voltage and full load current. Now the pulley, due to the net pull, due to the friction, that is W1 minus W2, you can get W2 minus W1 also, because this is irrespective of sign. Here we will take the modulated value into kg. So because of that, here we are getting that gravitation 9.81 into W1 minus W2 Newton. Now what will be the value of the shaft torque? That means this value should be multiplied by the radius of the pulley. So as per the shaft torque, it is represented here T suffix SH. SH because of the shaft torque. Now motor output power, that means P will be equal to omega T. It's a very common equation. I have discussed several times in laboratory that power P, that is equal to omega T. Omega means 2 pi n and T is here the shaft torque. So the correspondingly the equation becomes 2 pi n and it is multiplied by T sh. So here again we can put this value directly, 9.81 2 pi n into T sh in watt, and this again 2 pi n can be replaced by 2 into 3.14, that is multiplying this 9.81 and we are getting 61.68 n into W1 minus W2 into R watt. So as we have already connected a voltmeter in parallel and an ammeter in series with the input, so from there we can directly get value of voltmeter reading and ammeter reading, and multiplying this voltmeter reading with the ammeter reading we can get directly the value of the input power. So once we get the value of input power, from there we can directly calculate the efficiency, because here efficiency will be equal to output by input. So what is our output? This is specifically output as we have calculated. I have shown you in the previous slide. Now that will be divided by voltage into current, input voltage and current. Now from this test we can calculate directly the efficiency of the machine, but the method is not applicable in case of large size of motor. So for the large size of motor we are having some specific test procedure. One of them, or most important of them, is Swinburne test. So let us see what is Swinburne test and how it is conducted. So before starting this test, I just want to share with you that this test cannot be performed with series motor, because this test is performed at no load conditions. Specifically, please be careful here. This test is performed without loading, and this without loading condition cannot be conducted, or this test cannot be conducted with DC series motor. Why? Because from the characteristics of DC series motor, it can be concluded that in case of starting DC motor, series motor is having excessively high speed. So as a result, this motor cannot be run without loading. So this method is conducted in case of DC shunt motor or shunt generator. So in this case, here this is the variable resistance which is connected across the armature, and similarly this variable resistance is connected across the shunt field. This is the supply voltage, and if you see here, this point current is divided into two parts, and it will be passing through the shunt field, and rest amount of current that is coming input. That means if this is the motor case, this will be the input terminal, this will be your line current, and at this point it will be divided into two parts. One of them is passing through the shunt field, rest amount is passing through the armature. This current is fixed. Why this current is fixed? Because here the resistance, if this resistance is not varied, the shunt field resistance is constant, so this current will be correspondingly constant. Now in the next slide, I just already discussed with you why this cannot be performed with series motor. So here are a few advantage and disadvantage associated with a Swinburne test. So the advantage that this is economical, because no load, on no load the system is run. As a result, the input power is sufficient to perform the test, and the efficiency can be predetermined. That means we can calculate the efficiency directly. Okay. And similarly, it will be having some disadvantages, like the change in the iron loss from no load to full load cannot be considered, because basically I think all of you know iron losses are consist of hysteresis loss and eddy current loss. As a result, when the current changes, armature reaction, the flux distorted. What is armature reaction? The interaction between the main field flux and armature flux. So as a result, when the system runs from the no load condition towards the full load condition, the motor will try to compensate that higher amount of load. As a result, it will take much more current from the source, and as much more current it is taking from the source, that means armature current will be increased, and as the armature current increase, armature flux increases and it will interact much more with the field flux, and as the field flux and armature flux are interacting with each other, they will be much more distorted and it will increase the iron losses. Secondly, the stray losses, that means the constant field losses, cannot be determined in this test, and the efficiency in this case is overestimated. Thirdly, it's a very important factor that the temperature rise of the machine cannot be determined. So it may arise in your mind how the temperature rise is related to the efficiency of the machine. So if you run the motor for a long time, I think all of you have seen in laboratory the machine is heated up. The temperature rises, even you cannot touch on the upper surface of the machine. So what is the problem with this? So if the temperature rises, all of you have studied earlier, the rising of temperature is directly related to the resistance. So as the temperature rises, resistance increases, correspondingly the heat losses will be increases. So the rising in the heat losses, that cannot be determined from this procedure, and this is test cannot be indicated where the commutation will be satisfactory or not, that cannot be determined. So next to the Swinburne test. Swinburne test actual calculation, let us see. So here in this procedure, I0 is the no load current, ISH is the shunt field current, IA0 is the no load armature current. So which will be equal to I0 minus ISH in case of motor. V is the supply voltage, so no load input power, that will be equal to V into I0. Okay, so that means the voltmeter reading multiplied by the ammeter reading. So the no load input power supplies iron losses in the core, frictional windage losses and armature copper losses. So now let I equal to the load current at which efficiency we have to calculate. So IA, that means armature current, that will be equal to I minus ISH. If the machine is on motoring, this equation is true, and if the machine is in generating mode, in that case IA, that is equal to I plus ISH. Now efficiency as a motor. Now in case input power already we have calculated V into I. Now the losses across the armature, that is equal to IA square into RA, armature resistance, that will be equal to, in case of motor, I minus ISH from here, I minus ISH square into RA. So the constant losses, that will be equal to WC, that is equal to VI0 minus I0 minus ISH square, that means input power minus armature losses, that will be considering all the constant losses. Here this constant loss not only include the iron losses, it will including that constant losses, that means frictional and windage losses also. Here we cannot segregate them. Now the total losses will be here. This is the value of the total losses, and what will be the efficiency? Input minus losses by input, actually output by input. So output specifically input minus losses by output. So this is the corresponding input minus losses by input in case of motor. And similarly, this can be used for calculator of generator's efficiency. Here also output VI. Similarly, we can go for the same equation for corresponding armature losses. So the total losses will be here, and the efficiency of the generator will be output by output plus losses, which is equal to VI by VI plus WC plus I plus ISH square into RA. Okay. So thanks for all you for your patience hearing. If you have any question, put it in WhatsApp forum. Thank you.